Effective node pool management involves regular updates. Modify a managed node pool seamlessly using console, CLI, or API. Adjust properties of both node pool and worker nodes to ensure optimal performance and resource utilization. To edit a node pool property, you can click on the Edit button. This opens up the Edit Node Pool page. Here you can change the node pool name. You can also change the node pool count. You can decrease the number of worker nodes or increase them. You can change the node pool placement configuration details, as well as change the shape and image information of the worker nodes running in the node pool. But make a note that updates to the node pool properties only apply to worker nodes created after we save these changes. That means only the new worker nodes will be created with these updated changes. And if you want your existing worker nodes to be updated, you must click on the cycle nodes on the node pool detail page to replace existing nodes with updated properties. I'll click on cancel here for now. Here is the button to cycle nodes, with the help of which you can apply the updated properties to the existing worker nodes running within the node pool in your cluster. Updating the properties of a node pool is easy, but any changes made to the node pool properties only apply to new worker nodes, which means that existing nodes aren't updated. You need to either manually update a fleet of nodes or write your own scripts to do it, which contributes to regular operational toil. You can use the cycle nodes feature, which triggers the replacement of all existing nodes in a node pool with nodes running updated properties. All you have to do is simply modify the properties of node pools in the same way that you always have, and then cycle the nodes in the node pool. When we click on Cycle Nodes button, in the Cycle Nodes dialog, we can specify either integer or percentage values for the maximum number of nodes to add to the pool, that is the max surge, or have simultaneously unavailable, that is max unavailable, during the cycling operation. If you leave both the values blank, max surge is set to 1 and max unavailable is set to 0. For now, I'll click on cancel. We will cover modifying worker node properties in more detail in the upcoming lesson. When it comes to reducing cluster size, deletion becomes crucial. Remember, deletion is permanent and there is no option for recovery. To delete a managed node pool, you can use the console, the CLI, and the API. Let's see in demonstration how to delete an existing node pool. To delete a node pool from your Kubernetes cluster, click on the node pools in your resources section. And from the list of the node pools, click on this drop-down button. Go to the Actions menu and click on Delete Node Pool to delete the pool. Alternatively, click on the node pool's name and select the Delete Node Pool button to delete the pool. Reconfirm the deletion by specifying the pool name and click on Delete. Once you click on Delete, the node pool delete operation has started and you can notice that the node pool status says deleting. This will take some time before this node pool is deleted and the node pool number is set back to 1. We can keep a track of the node pool delete operations by clicking on the work request section. And as you can notice, we have the node pool delete operation in progress. Alright, after a while, the node pool delete operation is successful and the status says succeeded. Let's go to the node pool section. And here we can confirm that pool 2 has been deleted. Let's delve into advanced options for deletion. We introduce control by specifying when and how to cordon and drain worker nodes before termination. The eviction grace period allows setting a time frame for this process. Additionally, you can force terminate worker nodes at the end of the eviction grace period, ensuring effective management even in complex scenarios. For example, if we want to delete pool 1 from this cluster, I'll click on this drop down, go to the actions menu and click on delete node pool. Here I will specify the pool name to confirm deletion. I can either stick to the default settings or explore the advanced options. Under the advanced options for the cordon and drain preferences, we must set the eviction grace period. This is the time allotted for worker nodes to gracefully shut down before termination. We can choose the default 60 minutes that are allotted or customize it. Additionally, we can decide whether to force terminate nodes after the grace period. This is a choice to ensure termination even if cordoning and draining aren't successful. Select or deselect this option based on your termination preferences. For now, I'll click on cancel. As we wrap up this exploration of node pool management, we've gained insights into creating, listing, getting details, updating, and deleting node pools. Thank you for your attention, and I look forward to our next lesson. Hello and welcome to this lesson on modifying node pool and worker node properties. I am Mahendra Mehra, your senior OCI instructor at Oracle University. Let's dive in. As we explore the realm of node pool and worker node properties, let's understand the aspects you can modify to tailor your environment. You can customize the name of a node pool for clear identification. You can specify the version to run on new worker nodes. You can also adjust the count and define placement in availability domains, fault domains, and subnets. You get to choose the image for new worker nodes and define the shape for new worker nodes. You can also set boot volume size and encryption settings for new worker nodes. You can specify termination strategies for worker nodes by setting cordon and drain values. With the help of Cloud Init script, you can define the script for instances hosting worker nodes. And you can also set the key for accessing new worker nodes within your node pool. Now let's transition to OCI console to put our knowledge into practice. I'll guide you through a live demonstration of the concepts we've just covered in modifying node pool and worker node properties. Let's dive in and explore these actions in the actual OCI environment. I've already logged into my OCI console and this is my OCI dashboard. I'll click on the Kubernetes clusters from the recently visited section. Let me choose this OKE cluster for our demonstration. And since we are talking about modifying node pool and worker node properties, I'll go to the node pool page by clicking on the node pool link in the resources section. This cluster has only one node pool associated to it, which is pool 1. I'll click on the pool name. And this brings me to the node pool details page. And as discussed in the lesson, you can click on edit. This opens up the edit node pool page where you can edit the node pool name. We can scale up or scale down the number of worker nodes in the node pool by changing the value here. You can also change the node placement configuration by specifying a different availability domain and fault domain. You can also change the subnet in which to place them. But one thing to remember is that any change we make to the worker node properties will only apply to new worker nodes. We cannot change the properties of existing worker nodes. If we want the changes to take immediate effect, we should consider creating a new node pool with necessary settings and shift work from the original node pool to this new node pool. You can also change the shape and image for the new worker nodes. You can change the security rules for the new worker nodes. You can change the boot volume settings. You can change the boot volume and encryption settings for the new worker nodes. Under the advanced options, we can also set up the cordon and drain settings and Cloud Init script for the new worker nodes. You can also add a new SSH key to connect to your new worker nodes. And as the information here says, update to the node pool properties only apply to worker nodes created after we save these changes. And just in case we want all the nodes to be updated with the new node pool properties, we must click on the cycle nodes button on the node pool details page. For now, I'll click on cancel. Here is the cycle nodes button. We'll be discussing this feature in the upcoming lessons. I'll now switch back to the slide and continue with our lesson. As we navigate the intricacies of modifying node pool and worker node properties, keep these tips in mind. You should preserve system integrity by refraining from altering auto-generated names provided by Container Engine for Kubernetes. It's crucial to note that any modification in properties will impact new nodes exclusively. For immediate results, create a new node pool and migrate your work. For comprehensive updates such as OS upgrades, initiate a new node pool with your desired settings, utilizing kubectl drain for seamless migration. Be cautious when altering placement configurations, as it may result in terminating existing nodes and creating new ones in different locations. When utilizing the API for property updates, exercise caution and be aware of the potential worker node properties out of sync issue, along with its available workarounds. Steer clear of using kubectl delete node for scaling down. Maintain your desired node count by adjusting node pool properties through the console or API. To conclude this lesson, we've explored the intricacies of modifying node pool and worker node properties, covering key considerations and tips for effective management. Thank you for your attention, and I look forward to our continued learning journey. See you in the next lesson. Hello and welcome to this lesson on managing a worker node. Let's get started. As we dive into the intricacies of managing worker nodes, let's explore key tips and considerations to ensure a smooth process. When deleting a worker node, it typically removes the nodes and scales down the node pool by one. However, you can delete a worker node without scaling down using the CLI or API. The termination of worker nodes is determined by cordon and drain options. Note that these options are not supported with virtual nodes. Worker nodes are also deleted during scale downs and changes to placement configurations. Once marked for deletion, worker nodes cannot be recovered, even if the initial delete operation fails. The next update node pool operation attempts to terminate the node again. Worker nodes have auto-generated names. Avoid changing them to prevent manual deletion requirements if you delete the cluster. Remember, you can delete worker nodes using the console, the CLI, and the API. Now let's delve into configuring the instance metadata service, also abbreviated as IMDS, for Kubernetes clusters. IMDS is a valuable resource offering comprehensive information about running instances. This includes intricate details like instance specifications, attached VNICs, multipath enabled volume attachments, and custom metadata. Accessing instance information is facilitated through the console's instance details page or by logging into the instance directly utilizing the metadata service. IMDS is made accessible through an HTTP endpoint listening on IP address 169.254.169.254 on every instance. For heightened security, especially when dealing with IMDS, consider upgrading applications to utilize IMDS version 2. Additionally, disable requests to IMDS version 1 when supported by the image, aligning with best security practices. Let's explore how to utilize the CLI to disable the instance metadata service IMDS v1 endpoint on compute instances. This process is crucial for enhancing the security of our infrastructure. To achieve this using the CLI, particularly when creating a new node pool, we employ the OCICE node pool create command and pay close attention to the double-node-metadata parameter where we specify our legacy IMDS endpoints disabled with the value true. Executing this command effectively disables the IMDS v1 endpoint, contributing to an enhanced security posture for our Kubernetes worker nodes. When it comes to updating an existing node pool through the CLI, we utilize the OCICE node pool update command and pay attention to the double-node-metadata parameter where we specify our legacy IMDS endpoints disabled with the value true. It's crucial to note that this action does not retroactively apply to compute instances already hosting existing managed nodes. The IMDS v1 endpoints on these instances remains enabled. I'll switch to the OCI console and we will see how to disable the IMDS v1 endpoint for an existing node pool in one of our Kubernetes cluster. Well, this is my OCI Kubernetes page and I'll be selecting the first Kubernetes cluster on the list. This cluster has one node pool and 3 worker nodes within it. I'll select the node pools and click on pool 1. Firstly, I'll show you that how to access information from the IMDS v1 endpoints. I'll select one of the worker nodes and I'll copy the public IP address of this worker node. I'll head back to our previous tab, open up the Cloud Shell terminal, and I'll SSH into this worker node using SSH OPC and the IP address of the worker node. As you can notice, I've logged in into the worker node. Now I'll try to get some information from the IMDS v1 endpoint by using the curl command. Now, this is the curl command to get information from the IMDS v1 endpoint. Once I hit enter, I get to see a lot of details about our Kubernetes cluster and the node pool details. It include informations like agent configurations, availability domain informations, compartment informations, information about the cluster like its display name, its cluster ID, its label, the OKE image used for the cluster. Also sensitive information like the SSH authorized keys is available at the IMDS v1 endpoint. I'll clear the screen here and exit out of the SSH session. I'll clear the screen again. I'll press Ctrl L. Thank you for watching. Welcome back. Let's resume from where we left off in the last session. I will now run the command OCICE node pool update where I provided the node pool OSID. The node pool OSID can be retrieved from the node pool's details page where you can copy the node pool ID from this location. I have already provided my node pool's ID here and the node-metadata parameter where our legacy IMDS endpoints disabled value is set to true. Well, the command ran successfully and a new work request has been created. Let's go to the work request section in the Kubernetes cluster and reconfirm. I'll minimize the Cloud Shell window and scroll down to the work request. And you can notice the node pool update work request has completed successfully. To confirm that this is the same work request, we can cross-check the work request ID. Here the work request ID ends with 2CQ. And if I go back to the Cloud Shell terminal, you can notice that the work request that was created has the same OSID that ends with 2CQ. Now, having updated an existing node pool, the IMDS v1 endpoint is disabled on compute instances hosting new managed nodes from now on. However, note that the compute instances already hosting existing managed nodes are not updated, and their IMDS v1 endpoints remain enabled. Now I'll minimize the Cloud Shell. Now just to ensure that this change has taken effect, what I'll do is I'll edit the node pool properties and add one more node to this node pool. Currently there are 3 nodes in this node pool, and the IPs are that ends with 149, 26 and 150. I'll click on edit. I'll change the node count value to 4 and click on save changes. Well, the node pool has gone into updating state. We will wait until the node pool is active again and we have the new nodes detail available to us. Well, our 4th node is almost ready and currently it's in the updating configuration state. Alright, our 4th node is up and ready. I'll quickly fetch the node's public IP address now. I'll click on the node's name. This opens up the compute instance details page. I'll copy the public IP address of our worker node, head back to the previous tab and restore the Cloud Shell machine. Now I'll SSH into this worker node using the SSH command, sshopc and the IP address of our worker node. I'll hit enter. As you can notice from the prompt, I've logged in into my worker node that I just created. Now to confirm that the IMDS v1 endpoint is disabled on this worker node, I'll run the curl command and hit enter. And this time we get to see a 404 not found error. This is basically when the IMDS v1 endpoint is not available on the compute instance, we receive the 404 not found error. This means we were successful at editing the properties for our node pool to disable IMDS v1. But remember, this only applies to new worker nodes within the node pool. If I exit out of this worker node and re-log in into the older worker node, let me copy the IP address of our older worker node, which is this, and SSH into this one and hit enter. As you can notice, I am logged in into my worker node that was created earlier before we added or updated the property. Now if I run the same curl command again, we are still able to access the IMDS v1 endpoint because the updated property has not affected the existing worker node. The changes don't affect or don't apply to the existing worker node. I'll now head back to the slide deck. Well, I've already covered this in the demo. To confirm the IMDS v1 endpoint is disabled, we must first connect to the compute instance hosting the worker node by using SSH. And then we must run the curl command to confirm if the IMDS v1 endpoint is disabled. When an IMDS v1 endpoint is not available on a compute instance, you receive an HTTP 404 not found error. In wrapping up, we've explored essential worker node management and deletion practices, ensuring optimal performance in Kubernetes environments. Thank you for joining this lesson. See you in the next lesson. Hello and welcome to this lesson on managing worker node capacity types. In Container Engine for Kubernetes, the capacity type you choose for compute instances hosting worker nodes affects workload availability and costs. Let's explore the choices you have when defining a node pool. First up, we have on-demand capacity. It's your default option where you pay for the compute capacity by second. Just keep in mind, there's no guaranteed capacity during large workloads. Next, we have reserved capacity. This is all about reserving capacity for future use, ensuring availability whenever you need it. When you launch instances against the reservation, the used capacity is returned when instances are terminated, and unused capacity gets metered differently. And finally, we have preemptible capacity. a cost-effective option for short-lived workload. These instances behave like regular ones, but be aware, they can be terminated when capacity is needed elsewhere. Let's dive into the lesson for a deeper understanding. Let's delve into reserved capacity. It's your strategic move to reserve compute capacity in advance, especially for critical events or those sudden workload spikes. When it comes to container engine for Kubernetes, using reservations ensures that your node pools tap into the reserved capacity. Here's a key tip. Make sure the placement of your node pool aligns with the specifics of the capacity reservation. That includes the instance type, availability domain, and fault domain. And here's a cool feature. Multiple availability domains in a node pool allow for different capacity reservations. Just a quick note to remember, any changes you make to the worker node properties will impact new nodes, not the existing ones. Let's talk about preemptible capacity, a smart choice for those looking to save cost on transient workloads or fault-tolerant applications. These instances behave just like regular ones, but with a cost-saving twist. They are terminated when the capacity is needed elsewhere. Container Engine for Kubernetes has your back. It safely evicts pods and tries to replace terminated preemptible instances. Keep an eye out for those automatic Kubernetes labels and taints. They are labeled as oci.oraclecloud.com/OKE is preemptible equals to true, giving you the control over pod scheduling on preemptible worker nodes. Remember, you are in control. Decide whether boot volumes are permanently deleted upon preemptible instance termination. However, be aware of limitations and compatibility requirements. And a quick reminder, any changes to worker node properties will affect new nodes only. Let's address the required IAM policies for using capacity reservation. Firstly, the user must belong to a group that has been granted permission to use capacity reservation, for which you should have the following policy in place that says allow group name to use compute capacity reservations in a given location. You can replace the location placeholder with your compartment name or tenancy. Next up, you must grant Container Engine for Kubernetes permission to launch instances using capacity reservations, for which you must set the policy allow service OKE to use compute capacity reservations in tenancy. This policy must be set at root level. In conclusion, mastering worker node capacity types in Container Engine for Kubernetes empowers you to optimize cost and performance. Choose wisely based on your workload characteristics and stay tuned for more insights in our next lesson. Thank you for watching. Hello and welcome to this demo on using capacity reservations to provision managed nodes. Let's get started. I'll transition to the OCI console. I've already logged into my OCI account and let's go to the Kubernetes cluster service page. I'll be using the first cluster on the list for this demonstration. I'll select the cluster. As discussed in our previous lesson, we need two IAM policies for using capacity reservations. I've already added those policies. Let me quickly show them to you. I'll go to the policies page by clicking on the navigation menu, go to the identity and security option and click on policies. Well, the user policy has been added in the parent compartment, that is Mahendra. If you notice, the OKE capacity reservation policy is created that allows my user group to use compute capacity reservation in the compartment CTD OKE. This is the compartment where I'll be creating the capacity reservation. And the other policy is set in the root compartment. I'll select the policies page. And from the compartment list, I'll select the root compartment. This is the policy that I had added. It says allow service OKE to use compute capacity reservations in tenancy. Now that you have noticed that I have both the policies in place, let's go to the Kubernetes cluster service page. Let me select the compartment, which is CTD OKE. And this is the cluster where I'll be performing the demonstration. At present, this cluster has only one node pool. I'll select the node pools. And as you can notice, this has one node pool with total of 4 worker nodes running in it. I'll quickly duplicate this tab. Now there are 3 ways using which you can specify capacity reservation for a cluster. One is while using the custom create workflow, and the other way is by editing the node pool properties, and the third one is by creating a new node pool. I'll show you how to edit an existing node pool property to specify capacity reservation. Let me select the node pool. Here I'll click on edit option. Now you can update a node pool node placement configuration to go for one of the available capacity reservations. Now before we proceed and update the node pool property to use one of the capacity reservation, we must ensure that the capacity reservation is already in place, right? So let's go to the compute instance service and see if we have a compute reservation in place. In the interest of time, I've already created the capacity reservation. I'll go to the previous tab and go to the compute service and click on capacity reservations. As you can notice, OKE-capacity is the name of the capacity reservation that's already created in the CTD OKE compartment. I'll click on the name. And you can notice the capacity configuration. The instance type is VM standard E3 Flex with 1 OCPU and 16 GB memory. The reserved capacity is set to 2, and the fault domain is set to FD1 for the availability domain AD1. Let's head back to the update node pool page. And as discussed in the lesson, we must make sure that the node shape, availability domain, and the fault domain in the node pools placement configuration must match the capacity reservations instance type, availability domain, and fault domain respectively. The capacity reservation that I have created is for AD1 and fault domain 1. In that case, I will select fault domain 1 here and click on show advanced options. This is where we get to choose the capacity type. And like we discussed in the lesson, we have 3 options to choose from. One is the on-demand capacity, the other one is capacity reservation, and the third one is preemptible capacity. By default, the on-demand capacity is selected, but we will go for capacity reservation. And here you must select the capacity reservation that's already created in your compartment. In our case, it's OKE capacity. As you can notice, I have created one capacity reservation for one of the availability domains. If we specify multiple availability domains in the node pool placement configuration, we can specify different capacity reservation for each availability domain. But remember, any changes we make to the worker node properties only applies to the new worker nodes. Updating the capacity reservation associated with a node pool will not impact the properties of existing worker nodes. For now, I'll click on cancel. I'll go back to the cluster details page. And like I mentioned, there's another way using which you can specify capacity reservation is when you're creating a new node pool. When I click on add node pool, this opens up add node pool page where I can specify a different name to this pool. And under the node placement configuration, I'll select the availability domain as per my capacity reservation template. Select the worker node, select the fault domain, which is FD1. go to show advanced options, and here I'll select capacity reservation. And from the capacity reservation in the compartment name, I'll select OKE capacity. We'll scroll down, and under the node pool options, the node count is set to 3. But remember that our capacity reservation says the reserved capacity is set to 2, which means we'll have to make sure that the node count should be less than or equal to the reserved capacity. Notice the shape and image for the worker node is VM standard E3 flex, which is similar to the one that we have defined in the capacity reservation. The number of node count, I'll set it to 2. For port communication, I'll select the worker node subnet, and I'll simply click on add to add this node pool, which is using the capacity reservation type, and the capacity reservation it's using is OKE capacity. And I'll click on add, which will add a new node pool to this cluster with the capacity type set to capacity reservation, and the reservation name is OKE-capacity. I'll click on the work request to check the status of the node pool creation. As you can notice, the node pool create operation is in progress. Now let's wait until we get to see another entry for the node pool, which is pool 2, using the capacity type as capacity reservation. Alright, after a while, we can see the new pool has been added to our pools list, that is pool 2. And if I go back to the capacity reservation page, we will notice that out of the 2 reserved capacity, we have both of them used, because the number of nodes that we had defined in pool 2's configuration was set to 2, which means the reserved capacity is all used. We can also use preemptible capacity to provision worker nodes. To use preemptible capacity, you can either update an existing node pool property, or you can click on add node pool and you can specify the details for the new pool. Select the availability domain and the worker node subnet. All domains are optional, and click on show advanced option. Here under the capacity type, we can select preemptible capacity, and we must check when reclaimed permanently delete the attached volume. This option allows you to choose whether to permanently delete the attached boot volume when the capacity is reclaimed. Also remember, if you specify multiple availability domains in a node pool placement configuration, you can specify different capacity type for each availability domain. Let's say for the first one we selected preemptible capacity, for the next one we select on-demand capacity, and for the third one let's select the worker node subnet, and for the third one let's say I select reserved capacity, that is OKE-capacity, although it's not available for now. Well, this kind of a setting is possible. However, Oracle recommends all worker nodes in the node pool have the same capacity type to make node pool management easier. I'll click on cancel. With this, we come to the end of this demo where we saw how to set up capacity type for different worker node creation. I hope you found this demo useful. See you in the next one. Thank you for watching. Hello and welcome to this lesson on using custom cloud init initialization scripts to set up managed nodes. Let's get started. Cloud init stands as the industry standard for initializing cloud instances, facilitating system provisioning for private cloud infrastructure and bare metal installations. Universally supported across major public cloud providers including Oracle Cloud Infrastructure. Cloud init executes scripts to initialize and configure instances. In the realm of container engine for Kubernetes, Cloud init takes center stage for setting up compute instances, hosting managed nodes. Each instance receives a default startup script, a critical component executed during the initial boot, incorporating essential logic provided by Container Engine for Kubernetes. This script forms the backbone of the configuration process, ensuring seamless integration with the Kubernetes environment. On the screen, you can see the default Cloud Init script which is used. You can customize the default startup script by adding your own logic to the script, either before or after the default logic. Customizing the default startup script enables you to configure an SE Linux policy on all worker node hosts for security and compliance purposes. It also allows to unassign an instance's ephemeral public IP on startup and reassign the instance a reserved public IP instead. It allows you to configure a corporate proxy, also configure custom YUM proxies, and install mandated antivirus software and other security tools. If you do customize the default startup script, make sure that you do not modify the logic provided by OKE. Also remember, you can customize the default startup script when creating a new cluster or when creating new node pools and modifying existing node pools. You can use the console, you can use the CLI or the API for this purpose. In certain scenarios, custom cloud init scripts prove invaluable, especially when configuring security enhanced Linux, also known as SE Linux on managed nodes. SE Linux acts as a robust security enhancement for Linux, empowering administrators to define resource access rules. SE Linux operates in two states, enabled or disabled, and when enabled, it can run in enforcing or permissive modes. By default, worker nodes run SE Linux in permissive mode, logging events without enforcing access rules. To enable access rule enforcement, you can use a custom cloud init script, and the script is shown on the screen. These are the lines that we must include below our default startup script. This script sets SE Linux to run in enforcing mode, actively blocking actions contrary to the policy. Upon execution, the script ensures SE Linux operates in the desired mode, providing administrators with a finely tuned security layer for their Kubernetes environment. As we conclude this lesson, harnessing the power of custom cloud init scripts adds a layer of flexibility and customization to your container engine for Kubernetes environment. Stay tuned for more insights in our next session. Thank you for watching. Hello and welcome to this demo on creating a custom cloud init script. In this demo, we will be setting up a cloud init script that sets SE Linux to run in enforcing mode within our worker nodes. Let's get started. I've already logged into my OCI console and this is my OKE cluster service page. And like I mentioned in the previous lesson, we can set up custom cloud init script in three ways. One is when we create a new cluster. You can click on create cluster, click on custom create workflow option and specify the cloud init script while creating the cluster. This is one of the ways using which you can set up custom cloud init script. Other ways using which you can set up custom cloud init script is by creating new node pools or updating existing ones. In this demo, I'll be creating a new node pool with custom cloud init script that sets SE Linux to run in enforcing mode. I'll be selecting the first cluster from the list. And as you can notice, it has one node pool with 4 worker nodes. I'll go ahead and click on add node pool. Give this pool a suitable name and I'll leave it to managed. Under the node placement configuration, I'll select availability domain and the worker node subnet and leave the capacity type to on-demand capacity. Leave the shape and image to the default selection. I'll reduce the node count to 1. Under the pod communication section, I'll select the worker node subnet and it's time to click on show advanced options. Here we have the initialization script section. where we can upload a file using the choose cloud init script option or paste the script in the text area. I will go ahead with the second option, which is paste cloud init script, and paste the customized script. Well, this is the custom script to enable SE Linux to run in enforcing mode in our worker nodes, where these are the two lines that we have added below the default script, where we have set enforce value to 1, and using the sed command we are setting the SE Linux variable value to enforcing in the SE Linux configuration file. If you want to create your own custom cloud init script, you can always download the custom cloud init script template and then modify the template as per your requirements. I'll also paste the public key to access this worker node. I'll go ahead and click on add. I'll click on work request here to check the status of node pool creation. As you can notice, the node pool create operation is in progress. Let's wait until we see a second entry for our pool 2 in the list. In the meanwhile, I'll open up a new tab. As you can notice, pool 2 is in creating state. I'll open up the Cloud Shell terminal. Now what I'll do is I'll SSH into one of the worker nodes running in pool 1 and check the SE Linux status. I'll click on pool 1 here to get the IP address of the worker node. Let me select one of the worker nodes from the list. I'll copy the IP address, head back to the Cloud Shell terminal, and let me maximize this. Let me run the SSH command and hit enter. Well, I'm logged in into my worker node, and I'll run the command get enforce to check the status and the mode of SE Linux that is running on the worker node. Well, from the output, it's clear that the SE Linux is set to permissive mode in the worker nodes that are already part of the cluster before we made the update. I'll exit from this worker node, and let's minimize the Cloud Shell and see whether node pool 2 has been created and attached to our cluster. Let me go back to the cluster details. Well, the node pool creation operation has completed. Let's check whether we have the node pool entry here. Let me do a quick refresh. Well, there you go. We have the entry for pool 2. Now let me click on pool 2 and go to the only worker node in the node pool. This is the worker node that was created based on the updated node pool properties. I'll go ahead and copy the public IP address and go to the Cloud Shell terminal. We'll SSH into this worker node now. Well, I'll type yes here and hit enter. As you can notice from the prompt, I'm logged in into my new worker node, which was created based on the updated node pool properties, where we had set the SE Linux to run in enforcing mode. Now I'll run the get enforce command. To check the status and mode of SE Linux on this worker node. Well, from the output, it's clear that the custom cloud init script was executed when the worker node was booted and the SE Linux was set to enforcing. Well, there are many other use cases for custom cloud init scripts that are available in the official documentation. You can find them here under Managing Kubernetes Cluster. And remember, when creating a custom cloud init script, like I mentioned, you can download the custom init script template and modify the script file as per your requirement. Make sure you don't change anything in the default logic. Just add your logic towards the start or at the end of the default logic. With this, we come to the end of this demo where we saw how to set up custom cloud init initialization scripts to set up managed nodes. I hope you found this demo useful. See you in the next one. Thank you for watching. Hello and welcome to our exploration of scaling Kubernetes clusters and node pools with Container Engine for Kubernetes. Let's get started. When it comes to scaling clusters with managed node pools, you have the power to adjust the number of managed node pools in a cluster for dynamic scaling. You can fine tune the number of managed nodes within a pool for granular control and embrace auto scaling, allowing automated adjustments to manage node pools and pods based on demand. Virtual node pools, a game changer in operational ease, offer automatic scaling with operational overhead managed for you. Support for up to 1000 pods per virtual node, eliminating scalability concerns. For further customization, you may increase virtual node pools or virtual nodes for cluster and node pool scaling. First up, scaling a node pool involves adjusting the number of worker nodes along with their placement in different availability domain and subnets. Remember, any changes made to worker node properties exclusively impact new nodes. Existing worker nodes remain untouched. When tweaking a node pool's placement configuration, brace yourself for a transformation. Existing worker nodes bid farewell, paving the way for their reincarnation in new locations. For those diving into capacity reservations, align the node pool's placement configuration with reservation requirements. It's the key to harmony. A golden rule: steer clear of the kubectl delete node command for scaling down or terminating worker nodes. Instead, gracefully reduce worker nodes through the console or API. In Kubernetes, scaling down a node pool hinges on key properties: cordon and drain. They determine when and how worker nodes are terminated, ensuring a smooth scaling down process. As we wrap up this lesson on scaling Kubernetes clusters and node pools, remember, flexibility is the key to optimizing your environment. Stay tuned for more insights in our upcoming lessons. I hope you found this one useful. Thank you for watching. Welcome to the dynamic world of autoscaling Kubernetes node pools. In this lesson, we'll unravel the capabilities of the Kubernetes cluster autoscaler and how it seamlessly adjusts node pool sizes based on application demands. So let's get started. The Kubernetes autoscaler acts as your dynamic helper, automatically adjusting node pool sizes to align with the changing demands of your application workloads. When resource constraints create hurdles for pod scheduling, the autoscaler swiftly adds nodes to ensure your applications run smoothly. On the flip side, it's equally adept at decluttering your environment by removing underutilized nodes, optimizing your resource usage for cost efficiency. It's important to note that these adjustments are resource request driven, not utilization driven. The autoscaler relies on specified resource requests, ensuring your applications get what they need. Configuring the Kubernetes cluster autoscaler is a breeze. Through configuration files, you specify which node pools to target, set minimum and maximum sizes, and define the rules for autoscaling. For the magic to happen, don't forget to include resource request limits in your pod specifications. This ensures the autoscaler has the information it needs to make informed decisions about resizing your node pools. Let's take a look with the help of an example how the cluster autoscaler works. Assume you have a cluster with the node pools where all the nodes are occupied running certain pods. Now the new pods are in a pending state. The cluster autoscaler senses this and requests for a new node. A new node is provisioned and later these pods that are in pending state are scheduled on the new node. Let's look at the two possible ways using which you can deploy the Kubernetes cluster autoscaler. I'll first talk about the standalone program. You must opt for the Kubernetes cluster autoscaler as a standalone program for full version compatibility. This allows seamless integration with your Kubernetes cluster. It allows to customize configurations to meet specific needs, maintain manual control over upgrades, and enjoy complete autonomy for a tailored Kubernetes environment. On the other hand, you can opt for the cluster add-on option. This simplifies your configuration management with the Kubernetes cluster autoscaler as a cluster add-on. You can benefit from automatic updates for seamless maintenance and effortlessly manage add-on versions to stay in sync with your cluster environment. This user-friendly approach strikes a balance between simplicity and flexibility, ensuring a hassle-free experience with essential customizations. Let's delve into key recommendations for harnessing the full potential of the Kubernetes cluster autoscaler in production environments. Always ensure there's at least one unmanaged node pool in your cluster to support critical cluster add-ons. This pool requires manual scaling and serves as a safety net for essential functionalities. For robust availability, configure multiple replicas for the Kubernetes cluster autoscaler in your configuration file. This redundancy ensures that even if one replica faces eviction, others can continue orchestrating node pool adjustments. In your configuration file, set max node provision time to 25 minutes. This precautionary measure accommodates potential variations in node provisioning times, particularly when adding multiple nodes simultaneously. Align the maximum node count in the pool with the tenancy limit for the worker node shape. The Kubernetes autoscaler won't create nodes beyond this limit, preventing potential conflicts. Optimize node pool management by using single availability domains per node pool, especially when the Kubernetes cluster autoscaler is in charge. This streamlined approach enhances efficiency. Design your applications to gracefully handle disruptions caused by the autoscaler, such as node removals or pod migrations. Utilize pod disruption budgets to ensure smooth transitions. At all times, maintain the expected behavior and consistency of autoscaler managed node pools by avoiding manual changes. Resist the temptation to alter nodes through kubectl or the console, as the autoscaler may override such modifications or alter its behavior. Let's explore essential tips and considerations when working with Kubernetes Cluster Autoscaler. The Kubernetes Cluster Autoscaler dynamically adjusts existing node pools within the cluster, avoiding the creation of new clusters, node pools, or pods. Ensuring compatibility with pod scheduling and eviction rules, the autoscaler won't remove nodes running essential kube system pods except for daemon sets or mirror pods. Fine-tune behavior using the skip nodes with system pods configuration parameter, offering control over the autoscaler's decision-making process. When using Terraform alongside the Kubernetes cluster autoscaler, leverage the Terraform ignore_changes feature to prevent conflicts in node pool size adjustments. Upgrade the Kubernetes cluster autoscaler manually when upgrading your cluster to a new Kubernetes version, as automatic upgrades are not supported. For smooth integration, the Kubernetes cluster autoscaler requires clusters created with OKE version 1.17 or later. It is compatible with the managed node pools but does not support virtual node pools. To wrap up, in this lesson we covered the functioning of Kubernetes cluster autoscaler. I hope you found this lesson useful. See you in the next one. Thank you for watching. Welcome back. Let's continue from where we left off in our previous demo. The next thing is to view scaling operation. Now we will watch the Kubernetes cluster autoscaler that we have deployed as it automatically scales worker nodes in our node pool. I'll navigate back to the OCI console and duplicate this tab to open up a new Cloud Shell terminal. I'll clear the screen. Now I've already defined a sample Nginx application. I'll go to the examples directory. This is my sample Nginx application, which is basically a deployment running 2 Nginx pods and fetching the image from our OCIR repository. And there's a resource request for memory that has been set to 500 MB. I'll close this file. Now I'll go ahead and deploy the sample application by running the kubectl create command. Well, the output says the Nginx deployment created. I run the kubectl get pods command and hit enter. And we can confirm that the 2 Nginx pods are up and running. I'll clear the screen. Now I'll increase the number of pods in the Nginx deployment by setting the replicas to 75. I'll run the command kubectl scale deployment, name of the deployment which is Nginx deployment, and set the replica flag to 75. This command will increase the workload on our Kubernetes cluster by increasing the pods from 2 to 75. I'll go ahead and hit enter. And it says Nginx deployment scaled. Now to view the status of the deployment, I'll run the kubectl get deployment command and append the watch flag at the end. Well, we can observe that the number of pods are getting scaled and it has increased the number of pods from 2 to 48 for now, and it has paused. That is because the number of worker nodes in our current cluster could only accommodate up to 48 pods. Let's see what the cluster autoscaler does now. Well, we can observe that the cluster autoscaler has already started a scale up operation to increase the number of worker nodes in the node pool and set the size of the node pool to 3, which was originally 2 worker nodes. To confirm the same, I'll go to the Kubernetes cluster and go to the node pools section. This is the node pool of our Kubernetes cluster, right? Pool 1. And as you can observe, the third worker node is being scaled up to accommodate the workload demands. Once this worker node is ready, we should be able to see the scaling up operation proceed. In the meantime, we observe that the cluster autoscaler has scaled up the node pool by adding another node to this node pool. And this node is again in the creating state. Let's check the log. From the log, it's clear that it has scaled up the node pool to size 4, which means to accommodate 75 pods, it is using 4 nodes. And that's pure math, as 2 worker nodes could accommodate only 48. To accommodate 75, we'll have to use 4 worker nodes. Let's check the node status. Well, both nodes are still not ready yet. All right, the scaling operation has resumed and again it has paused at 72. Well, the third node in the node pool is up and ready, which is why the scaling operation resumed, but now has paused to wait for the fourth node to accommodate the remaining pods. All right, the scaling operation has completed successfully as we have all the 75 pods up and running. I'll close this watch command and we'll run the kubectl get pods command. I'll use the -o wide flag. And as you can notice, we have the 75 Nginx pod up and running, and they all are deployed on separate worker nodes with IP 155, 179, 212, and 90. We go back to the Kubernetes clusters page and scroll down. These are the worker nodes that are hosting our Nginx pods. It's time to delete the Nginx deployment using the kubectl command. and hit enter. As you can see, the Nginx deployment is deleted. Now that I've deleted the sample Nginx application, the worker nodes that was scaled up by the cluster autoscaler now should have reduced to the original number. This operation will take some time. Let's head back to the cluster autoscaler logs. But remember from the lesson, the cluster autoscaler will not bring down those worker nodes that are running kubesystem pods. Just to confirm which worker nodes are running kubesystem pods, especially core DNS, I'll run the kubectl command. I'll use the -o wide flag which nodes are running the kubesystem, especially the core DNS pods within the kubesystem namespace. Well, from the output, we see that there are 4 core DNS pods running, and they're all running on worker nodes with IP 179, 212, and 90, which means there's only one worker node that is free of core DNS pod, whose IP is 10.0.10.155. Now let's wait and observe if the Kubernetes cluster autoscaler scales down the node pool and brings down that worker node. Well, if you observe, after some 10 to 15 minutes, the scale down operation has started, and the Kubernetes autoscaler is removing the empty node with the IP 10.0.10.155. And it is deleting the compute instance running the worker node. And the work request ID for the delete operation is present here. You can confirm the same on the console. And if you notice here, the node with IP 10.0.10.155 is now undergoing delete operation, and the node state is set to deleting. Alright, the worker node entry is gone now. And with this, we come to the end of this demo, where we saw how to install, configure, and use Kubernetes Cluster Autoscaler as a cluster add-on to automatically resize the managed node pools in a cluster. I hope you found this demo interesting. See you in the next one. Thank you for watching.